Hi, this is Alex from devstories.eu, Async IO, episode 8 of 20. You drop a standard threading lock into your async application to protect a shared resource, and suddenly your entire event loop freezes completely. The lock did its job, but it halted everything else in the process. To solve this without blocking the loop, we use synchronization, locks, and mutexes. An async.io lock, often called a mutex, guarantees exclusive access to a shared resource among asynchronous tasks. First, we need to clear up a common confusion. You cannot use a standard threading lock from the Python threading module inside an async application. A threading lock operates at the operating system level. If it cannot acquire the lock, it pauses the entire thread. Because async IO runs multiple tasks cooperatively on a single thread, blocking that thread means the event loop stops. No network requests fire, no timers tick. Everything freezes. An async IO lock solves this by being task safe, not thread safe. When an async IO task tries to acquire a locked mutex, it does not block the thread. Instead, it suspends itself and yields control back to the event loop. This allows other unrelated tasks to continue their work while the first task waits in line. Let us anchor this to a concrete scenario. You have an application with dozens of async tasks making external API calls. Your OAuth token expires. Two different tasks notice the expired token at the exact same millisecond. Without synchronization, both tasks will independently fire off a request to the authentication server to refresh the token. This redundant work can trigger rate limits or immediately invalidate the first token due to strict rotation policies. To prevent this race condition, you create a single async IO lock when you initialize your application. This lock object is passed to or shared among all your API tasks. Now, look at the flow. Task A and Task B both detect the expired token. Task A reaches the synchronization block first and awaits the lock. It successfully acquires it. Task B arrives a fraction of a second later and awaits the same lock. Because Task A holds it, Task B goes to sleep, letting the event loop handle other chores. When multiple tasks wait for the same lock, async IO lines them up. Once the lock is released, the event loop wakes up the first task in line. Task A securely requests the new token, updates the shared token variable, and releases the lock. At that moment, the event loop wakes up Task B. Task B finally acquires the lock. However, before making a network call, Task B checks the token again. It sees the token is already valid, skips the refresh step, releases the lock, and continues with its primary API request. The safest way to implement this logic is using an asynchronous context manager. In your code, you write an async with statement followed by the lock object. When the execution enters this block, it waits for exclusive access. When the execution exits the block, either normally or because an error crashed the task, it automatically releases the lock. You do not need to manually call acquire or release methods, which eliminates the risk of accidentally leaving a lock engaged forever. Here's the key insight. An async IO lock does not protect your state from other operating system threads. It protects your state from your own concurrent tasks stepping on each other while awaiting other operations. Thanks for hanging out. Hope you picked up something new.